Thank you, everyone, and thank you, Martin, for the introduction. So I hope you've had a good start to iDoug and you enjoyed your lunch. When I submitted this abstract back in, I think, February or March, I didn't realize there'd be quite so much AI going on. So especially I didn't realize we'd have Paul Zakopoulos with videos and Mario Brothers at the start. So I apologize if this is a bit of an anticlimax after all of that. My motivation for doing this is that about a year ago I started formally studying AI in kind of more academic setting, and as we were going through some of the tasks and some of the process, I realized that a lot of this, as a Db2 practitioner, a lot of this was familiar. It led me to kind of think, well, can we do this in Db2? And does doing it in Db2 address some practical challenges with data science? So hopefully in the next 50 minutes or so I can guide you through some of that and show you some examples of where Db2 can be useful. So from a topics perspective, it's really around kind of 5 central topics. Really the first one is around why is data such a hot commodity at the moment? I think we all kind of know why, but I think it's useful to go back over it. And also address that as some of the challenges around doing data analytics. And these are evolving. Some of them are practical challenges and some of them are regulatory challenges that are starting to evolve. I didn't put it in here, but it was an interesting thing to study over the last few months. Paul mentioned it this morning around ethics, and that's something that's going to be a really big thing in the future as well. But with those, I think relational databases, and Db2 in particular, because this is iDoug, has a big role to play in this and can bring a unique view, perhaps, that other data stores don't. And then what I wanted to do was go over how we can do some AI in Db2. So as I came across in a lecture recently, when we make, in AI, we make assumptions about data, we choose models, we infer values, we infer qualities, and that is actually the process of AI. So people think that maybe have a vision of AI that is doing something really cool, but actually the steps to AI, the processes of AI, are very much something that we can do in the database. And lastly, because much as I'd love to say that we could do everything in Db2, we can't. And the reality is that a lot of the work will happen outside of Db2 in another tool. So I just wanted to introduce a little bit about how Db2 can interact with Python, as Python has very much in the last few years has become the language for data scientists. So if we get a little bit onto the why is data such a hot topic, or as I put it here, the desirability of data. So the term artificial intelligence itself goes back to about, I think it was first coined in 1955. But the science behind it goes back longer. But in many ways you could say AI has been a 60-year overnight success. But in the last few years, there's been a big renaissance, a big development in the amount of research and practical applications of what can be loosely termed AI technologies. To the point where we're now seeing the viable general application. So we have seen specific applications of AI technologies in the past. So if you're familiar with the term expert systems, they were AI systems. But now we're looking at more general applications. And we see that in a lot of commercial spheres, in the likes of what we see from Google and Amazon, Facebook, Baidu, things around speech recognition, image recognition. But also, we see more general applications of taking those image recognition technologies and, say, applying them to a domain like medicine, where there's a huge amount of research. Why now, you might ask? Well, now, although the science is very well established, what we've had in the last few years is the confluence of huge data sets and also relatively cheap compute, because a lot of this takes a lot of processing cycles, so being able to access computing power relatively cheaply makes this practical. And from a recent perspective, I just want to draw attention to their recent. It's kind of from the late 2000s, 2010s, early 2010s. That's what I mean by recent. So even though we go back quite a long way, it's really kind of the last decade, 15 years, that we've seen this big upsurge. And because of that, and because of this general application, we have lots and lots of groups now think AI is the next big thing. We hear about it a lot. We hear about how governments say they're going to, AI can do things. Corporations are clearly adopting AI. You're getting the AI message from IBM quite a lot, but we're not the only ones. Pick any of the FANG companies, and they're all employing AI in some way, greater shape and form. But equally, huge upsurge in research, which we'll talk to. And it's all about this idea of transformative change. So it's not just step change, not just advancing a process, it's something that is absolutely transformative. And that comes in the form of things like autonomous transport systems, not just cars, but transport systems. Things like medical diagnostics, personalization. They're all applications of AI, and actually they are both transforming our society as we understand it now. We only have to look at the scandals around Facebook and fake news and Cambridge Analytica to see how that is influencing democracy, but also how it might influence things in the future. And there's a lot of examples of that. So, say from the medical diagnostic side, one of the things is we have experts, AI-trained systems, deep neural net-trained systems, that are statistically as good as the very best specialists in the world. So you can take the capability of maybe the top 10 specialists in the world, and you can put that power in the hands of any doctor. And particularly in poorer countries, in second and third world countries, where they don't have access to that to that level of skill, or if they do, it's at a cost that nobody can afford. That kind of thing really is transformative. You can, there's been a lot of research, as an example, around diabetic retinopathy. Being able to diagnose that with a smartphone, by taking a picture of an eye, to give access to people who would never see a doctor, but to give them access to the capabilities of the best ophthalmologists in the world. But all of this, keeping pace with all this, can be very, very difficult. The number of papers in AI-related research has increased by about 7-fold since the late 90s. So AI has had a lot of what were called AI winters. So there was lots of peaks of interest and the trough of disillusionment, but it's had a few of those where they've died off. But over the last decade, we've seen this, or 15 years, we've seen a 7-fold increase in papers, and that pace is accelerating. So keeping up with all the developments can be very hard. And there's also an issue of fact versus fiction. So we've had cases, and there was one I came across recently where Facebook put out some text results from where they had bots talking to each other, or also generating text. Every now and then the bot would, we might term it as a crash, not really a crash, but it gets stuck in the loop with text. It would go, me too, me too, me too, me too. 24 hours later, there were stories on social media and some papers saying, Facebook is rewriting English. So we get this kind of fact and fiction thing. So what I would suggest in that is just caution you to say, stand back a little bit, but don't be scared by it. It's, AI is daunting, it's big, but there's huge practical applications, and it will come and it will change. But whether it's at the pace that my company and other companies want to believe, that's another thing. To get back to the basis of it, AI isn't magic. It has a very, very strong basis in mathematics, and specifically applied statistics. So depending where you want to draw the line, you can go all the way back to Aristotle with some of the basic philosophical underpinnings. But a lot of the maths is from the 17th and 18th century, so calculus, probabilities. So it goes back to the likes of Newton and Leibniz and Laplace and people like that. So while we're applying it in new and different ways, we actually do have a very good understanding of the science behind it. But the other thing as well, I think, about AI, and it'll apply, I think, a lot to us as people who work in corporations and organizations, is that while there'll be lots of cool, eye-catching breakthroughs, so autonomous cars is something people rave about, it'll be more mundane tasks. It'll be automating business processes, like credit checking is a classic example, or predicting prices, any kind of optimization problems. They are actually all fall into the category of artificial intelligence, and they are the things that will have power to change an awful lot of relatively mundane tasks, make them either obsolete from a human perspective or just augment what people can do. And augmentation is another big topic around this as well. So clearly, to do all this, data is the key. Data is the fuel by which all this runs, and it'll help us move from this time of where AI has been a kind of a niche topic. It's the data combined with the compute that is allowing us to move into this kind of summer of AI, or future of AI. So it is worth noting, though, that while for some people it's the oil of the new economy and the natural resource of the new economy, there are others in research, particularly who are concerned around ethics, who would see it as snake oil. And that comment is actually from a researcher called Stuart Russell, who is very, very well-known AI researcher in the University of California in Berkeley. And his issue with that is around amassing data with no clear purpose. And it is something that probably we all at a practical level with DB2 have to be concerned with, which is it's great to capture data, but do you really need it? We're used to the idea of purging data after a period of time or aggregating it because its use is dropping off, and there's a little bit of that in there. From a terminology point of view, I just wanted to clarify on this one because I think a lot of the terms get interchanged, and it's not always clear what people mean, but there's kind of a hierarchy. So really, anything that can be described as a generalized machine intelligence can be described as artificial intelligence. And by generalized, I don't mean that it's, kind of an all-knowing AI that is, going to wipe us out, Skynet or anything like that. But it's more that anything that a person can do that would make, that if we looked at a person and if we watched them doing something, anything that they do that we think makes them look intelligent, if a machine can do that, well, that's artificial intelligence. And it can be very simplistic, but that's what it really means. AI can also be defined as broad in that it has widespread general application across a number of domains, or it can be narrow in that it's very focused on a specific task or specific domain. But within AI then is the concept of machine learning. So both machine learning and the newer technology of deep learning, the newer philosophy of deep learning, they're both mechanisms for doing AI. They're not different to AI. They are AI. But really, there is a bit of a difference between them in terms of both the computation and the complexity that's involved. So machine learning, or ML, as you will see it referenced quite a lot, is about identifying patterns from the data, learning the data, essentially establishing some class of formula that allows us to make a prediction. And it really is written down and studied as a mathematical formula. It can be simple as y equals alpha x, where you're figuring out what the alpha is. X is your set of parameters, y is your outcome, and alpha is what you're trying to figure out. And what machine learning does is it works out what your value of alpha is. And in that sense, we don't program AI, we train AI. And there are huge amounts of statistical methods to do this. Some of them are iterative, that takes a number of computation cycles. There are some really powerful ones. Linear regression, if you've heard of it, is actually a one-step learning algorithm and can be remarkably effective across a lot of problems. Deep learning, on the other hand, is what's driving all of the current interest, the renewed interest. And this is something that really emerged in the late 2000s. So even though the research goes back into the 90s, some of the practical applications came along, started to emerge in the late 2000s. And then in 2014, there's a competition called ImageNet, where the purpose of ImageNet was to take a bank of images and have a neural network classify them. And it was in 2014, a team, I can't remember the first guy's name, but one of the associated professors with it was a guy called Jeffrey Hinton, who had that quote about machine learning. They developed a neural network that for the first time exceeded the capability of a human in terms of a classification of images. So without any training, with training, but without any prior identification of what the categories of image were, it outperformed a human. And that's really where what sparked a huge step change in deep learning. And we use it for things like feature identification, feature extraction. So on Paul's video this morning, when he had the video going around, or the tracking video of football match, where it was highlighting different advertising hoardings or highlighting different players, that's segmentation, that's feature extraction. So that's kind of where deep learning kicks in. And really, machine learning is where a lot of companies are going to get a lot of benefit from this, because it's practical business applications and it's relatively quick time to value. And it's deep learning where we'll start to see these new advancements like autonomous driving and autonomous transport. And actually, what we'll see is that it'll be a lot of systems combined. It won't be one single neural net that delivers all this. It'll be a combination of capabilities that will deliver this.
Just a question.
Yes.
Data classification in terms of classify my customers based on revenue.
Mm-hmm.
A, B, and C customers,
Mm-hmm.
just based on revenue. Does this help?
Well, it can. It depends on the question, really, and it depends on what you're.
If I define the classes,
Hmm.
just put my customers in one of fixed
Hmm.
defined classes, then I think it's not a dynamic clustering, but a fixed classification is already deep learning.
I wouldn't count. So, just for the recording, the question is if data is already classified, is it deep learning?
Yes.
It's not. I wouldn't call it deep learning. I would say that it's an application for machine learning, and it might be that instead of saying I've already classified my customers, that's fine. But the next question might be, given my class of customer and certain other parameters, what are they likely to buy? How much are they likely to buy? They're machine learning problems, and that's where we would say perform a regression analysis to say, well, in the start we might have a class. If we hadn't classified them, we might use an unsupervised learning technique to generate the classification for us. The next question might be then, once I have classified them, how are they likely to behave in response to certain questions or certain tasks?
Okay, thank you.
No problem. So the diagram on the right there, the squares, you might have seen something similar before from us, probably better drawn. This was my humble attempt with PowerPoint. And I know I just said it a minute ago, but I think it is really worth repeating that data is key. And it's obvious, but it's also what makes it relevant to Db2, because we are the people who have the data. And to achieve these things that really power AI, we need volume. We need volumes of data. We need variety of data. That's very important too. If we have data that comes from too narrow a data set, it means that our algorithm is only, our AI is only valid in a certain set of circumstances that happen to match that data set. Veracity is all about the data quality, because we need to be able to trust what we do with this algorithm. Whoop. We've lost the screen here. We can search for anything we want, but if we can't trust the data, or we can model anything we want, but if the data is not reliable, then the model is useless. Velocity is less of an issue with AI, but it can be. And one of the things that comes up, I don't address it here specifically, but you might see it in other presentations, is around how quickly the underlying basis for your model changes and how you change your model accordingly. But if we look at some of these things first, if we look at quantity, so really having large quantities is really what it's all about, because we will always have, and mathematically we always have noise. So we'll always have elements in our data that don't match any particular model, and we have to account for those. We can do our best to reduce them, but as with any process, we're measuring, and any measuring is a sort of an imperfection. We never have a perfect view of whatever model, whatever the real model, the reality is. We might also have outliers. So outliers are data that don't fit the model. And there's two ways of looking at them. They're either wrong, because we measured them wrong, or it might be something that we haven't actually considered before. They might be valid. So as a quick example, if you have a measure, say, of average customer balances in a bank, if the average balance is, say, $500 or €500, if you have somebody who's got €20,000 in there as their average balance, that's an outlier. It's not invalid data, but you have to then decide whether it's valid for, should I exclude it from my data model or not. Quality is probably the biggest thing that impacts AI. And data scientists talk about the 80-20 rule. So that's, they spend 80% of their time wrangling the data, or munging it, or preparing the data. They spend the other 20% of the time complaining about the data. That's either inadequate or they haven't done a good enough job preparing it. But it's where a huge amount of the effort goes. And another thing that's becoming, I think, more and more relevant, and particularly here in Europe, is around access to the data. So there's two ways to look at it. One, if you have a large data set, it takes time and effort to move it. But another thing is governance. And when I started hearing the governance story a few years ago, I probably, as a Db2 guy buried in Db2, I didn't think as much about it. But regulation like GDPR, things like that, means that you need to have a good reason to start shifting data out. You need to be able to trace where that data went, how it was used. You need to be able to explain how a model works. So they are things that, you know, aside from the technology aspect of it, they are very practical reasons why you might not want to move your data out of the database because you have restrictions on really being able to do that. So with that said, how can the database help? And this is where we get to why is a relational database a really good source for this, and why I think Db2 can be a powerful tool in this. Well, we have data models which impose some level of consistency on the data. We have referential integrity, we have constraints, things like not null, the amount of data you get in where there's gaps in the data, and you have to infer a value. When you infer a value, you're making your model less accurate. We have things like constraints like not null constraints. So we know there's an actual value, and we know that value has meaning, or hopefully has meaning. We have data glossaries, so we can explain what something means. If you get a data set in that's a CSV file just as a header, you may not know exactly what it means. So you're trying to decide whether that's important or not. Generally speaking, because of all these things, because we trust where the data came from, we trust the flow that arrived, we know the source system, we have a high degree of trust in our environment. And as we know, we also have the volumes. We have terabytes of data, tens of terabytes of data. You may not need all of it, but we have huge amount of data that we can generate a realistic sample from. And the last thing there is that Db2 in particular has some data science capabilities built in, which I'm going to touch on later, that explain or that allow us to address some of these access issues. So instead of bringing Db2 data to the data scientist, we can bring the data scientist to the data and have them operate and do some of their tasks there. And really, when we take that, we have quality and quantity and access, and I'm going to talk about locality briefly now as well. But all that allows us to generate a faster insight, or faster time to value with this. On the locality, and I really should have swapped these around, these graphs were generated from testing done a few years ago. Now, I can't remember all the details. I couldn't find my original source slide where I had all the details noted. But if you look at it, this was about originally generated for bringing some data to Spark jobs. But I think what it shows is that from a time-saving perspective, it's very much faster to operate on the data where it's already placed rather than moving the data around. Even in an optimized scenario, it's faster to move it around. And in an unoptimized scenario, as we have on the right there, it's significantly faster, orders of magnitude. But as I referenced earlier, we also have issues around, depending on the volume you have, you need a lot of storage or extra storage. There's governance around that. There's security implications around that. There may be business process arrangements around that, around getting sign-off to have access to bring the data to a new location, even if you addressed the other practicalities. So that kind of covered the why data is hot, why a relational database has something to offer on this. So I'm getting towards how we can do some of this in Db2, but what I just wanted to go through briefly was this concept of exploratory data analysis. So this is the 80%, is what a lot of what the time gets spent on. So lots of things happen in EDA, lots of data movement, lots of data manipulation, lots of data analysis. But really what it's about doing is making sure that the data is suitable for training purposes. So what I should have mentioned better earlier was we always talk about training, we talk as well about validation, and we talk about test. And if you were at Kelly's presentation earlier, he had a very good chart on how we split the data out. But we train our model on data, but the real value of our model is how well it works on unseen data. That's our test set, and that's our generalization. But we're all about to make the real application of the model work, we have to make sure our training data is suitable. EDA is also about getting a sense of what's coming, what your data looks like. And does your data actually really support the hypothesis? Because you always go in, you don't necessarily take data and kind of go, I'll just have a quick look at the data and see what it spits out. You usually have a question you need answered. You have a hypothesis over what this data is going to show you. So EDA is all about establishing that the data you have is going to support that, and that the data you have doesn't have some kind of mad characteristics that won't make sense, that all the ages are over 200, because that clearly isn't going to happen, or that all the date values are too old or something like that. It can be mundane stuff like that, but it's really about just making sure that the data is is trustworthy and that you can build a model with it. So there's a couple of tasks we do in that. So we can do patterns. We can look for patterns in the data. We can do imputation, where we say we don't have values for everything, but let's look at something like, I don't have the education level of everybody in my population, but I can infer it. I can say something as simple as the vast majority of people have a high school equivalency, or they have a bachelor's degree or something like that. So for anybody I don't know, I'll just assume that's the value. Or I can say, well, I'll actually break that down a little bit further. I'll say all the males under 40 have this level of qualification, females over 40 have this level of qualification. We can break it down whatever way, but that's what we mean by imputation. I mentioned outliers earlier. We can discuss them. We can decide what we're going to do with outliers. With clustering, if we've clustered people already, great. But we can also do another analysis of the clustering and say, is my cluster model correct? Are there other clusters of data here that would make sense to model or that I don't understand yet? And we can do things, a fundamental thing here as well is what we call dimensionality reduction. So every parameter you have in your model is a dimension. So age is a dimension. Gender, income, address, they're all dimensions. Every dimension we have adds to the mathematical complexity. So if we can reduce the number of dimensions, then what we end up with is a smaller model that we have to compute. And really, I couldn't get a picture for this one. But whether it's mountain climbing or any other journey, you could just start. You can just start climbing, you can just start driving. But it's better sometimes if you have an idea of the route that you're going to take. Am I taking the rocky route or am I taking the path up the mountain? So I kind of covered some of this a little bit there as well. Talking about the quality of the data. And some of these tasks will look very familiar to a DB2 professional. What does my data, does it have integrity? Do I have missing values? Are all my data types valid? And these are the things, again, that the relational database enforces. You won't end up with a string in an integer column. You can have it the other way around maybe, but that's a different story. What are the distributions of my data? Are they distributed in a normal Gaussian distribution? Are they some kind of strange distribution? Do they have no distribution at all? Do they look random? We can also look at engineering new features as well. We can maybe combine features that are of interest. So those are some of the tasks in EDA. But DB2 does some of these as well. And this is where we start getting to what can DB2 bring to the picture. So DB2 is capable of doing a broad range of tasks that are involved in data science. So standardizing values. So by standardizing values, we say that for computation reasons, we want all the values to be between 0 and 1. So there's algorithms that do that and ensure that that's done in a mathematically sound basis. So that's what we call standardization or normalization. DB2 can do that for you. It can do a certain amount of imputation. It can do, as we have in the diagram there, it can do a certain amount of binning. So it can generate histograms for you so you can get a view of the distribution of the data. It can do clustering. It can do dimensionality reduction through principal component analysis. And that diagram down there is an example of a PCA chart, a PCA plot. I'll explain that a little bit more later. But it has lots of statistical capabilities that are included in DB2, and which we can augment in DB2. So you can do some of this AI pre-work in DB2. So I'm going to show a quick example of doing a PCA. So this example uses what are called the in-database analytic extensions. So these are available in DB2 Warehouse, the containerized image. They're available in the Warehouse on Cloud image. I don't think they're yet available in the on-premise release. That said, it's as easy to deploy a warehouse on-premise as any other model. So in this example, we're calling IDAX PCA, so it's a stored procedure. The example here is actually from a Kaggle competition. If you're not familiar with Kaggle, it's a website, it's a community that does AI competitions. And one of the examples that I worked on myself for a while for an assignment was around some data that was generated on the quality of wine generated in a specific region of Portugal. And really it rated about, with 10 different parameters, the goal was to predict what was the quality of the wine as rated by experts. So what we have here as an example is we say, this is the model we have. The wine quality red is the source data up here. Sorry, I keep forgetting I have a pointer. We have an ID column. We just say what our ID column is. We tell it to send, these are specific attributes of the PCA model, so we tell it to center the data and to scale the model, and that's really about what I mentioned earlier about normalizing the data. So that's making sure that it's mathematically sound for computation. So it's steps you don't have to do. And then we just say, here's all the columns I want to use. So I've given it 10 columns, and I've asked it to give me a PCA reduction of this. So as I mentioned earlier, what we're trying to do with dimensionality reduction is we're trying to say, I have these 10 parameters, but I don't believe all these 10 parameters are needed for my model. So can I find a set of parameters that is much more compact? And that's what we do with PCA. So we execute our PCA model, and then we can get the results from it. And what we do with this is, with the PCA, is we look at two things particularly. We look at these values here, the proportion of variance and the cumulative variance. So lots of numbers. Easiest way to do it is to look at a chart. And I'll talk to the chart on the right first, which is this is plotting the values that were generated by Db2. And what we have here, these are the different values that we saw on the previous slide under proportional variance. And what they do is they say this value here explains just under 30% of the variance in the data. And this value here is just under 20, and so on. And the cumulative chart just says, as I go up the chart, as I add all these components together, I get to a point where maybe 80 or 90% of the data can be separated by just using these 5 components. That means I don't need to worry about the others. I can exclude them from my model because I don't need them anymore. That's an example of an EDA process, and it's something we did in Db2 without ever taking the data out of Db2. Now, if you have much more sensitive data, say personally identifiable data or commercially sensitive data that you just don't want a data scientist to leave on their laptop, you can have them do some of this work in Db2 beforehand. And then they take a smaller data set and perhaps an anonymized data set out of the database first. For comparison, I put the same data set through scikit-learn, which is one of the more popular models for data science. I just reran the same thing, and it was exactly the same. The results were exactly the same, which is kind of expected because PCA is a mathematical algorithm, but it was reassuring to see down to the 10th decimal place that Db2 gave exactly the same values as the most popular open source tool for this.
That doesn't run on ZOS,
It's not there on ZOS at the moment, no. No, it's, well, actually, I don't know on ZOS. I don't know if ZOS has these IDEX functions, but I don't think so. Jane, you know, no? Okay. So that was some EDA tools, but we have another of more kind of predictive capabilities in Db2 as well. So we have algorithms for regression and classification in both supervised and unsupervised forms. And Paul referenced this earlier, but really what we come down to two things. In regression, we're trying to predict a value, future sales. You know, what will that price of a house be? What's the average age at which somebody does a certain task? That's a regression. We're trying to plot a specific point. Classification is where we simply say they're on one side of a line or on another side of a line, whatever it is. So that's they belong to one kind of cluster or not another kind of cluster. That's classification. So Db2 supports simple linear regression, which is up here, and that can be a very simple y equals something to the, you know, x to the power x multiplied by something else gives you an output. We have generalized linear models, where we can do it with multiple parameters. We have lots of classifications, so k nearest neighbors is an example, where we say, given this data set, who's it most like? Of a given number of clusters, who's it most like? We do decision trees, which can be extremely powerful as well. Naive Bayes, which is a probabilistic model, where we include the idea of uncertainty. So we can say, I can say a value up here is, you know, I can say it goes, I'm predicting the value is going to be up here, but how certain am I? Am I only 50% certain? Am I 80% certain? 90% certain? And that's where we use something like a Bayesian algorithm instead. And that, we call it naive because it assumes that everything is independent. But there are some capabilities that are built into DB2 that we can take advantage of. But if we want to do more advanced AI, things that are not included in the standard DB2 model, there's a few ways to do that. The great thing is, because a lot of AI and a lot of ML is actually just mathematics, you can write your own SQL functions to do it. As I said earlier, it's not magic. Sometimes it appears that way, and when you're looking at the equations, or as I've been looking at the equations, I've been going, I don't understand how that works. So it appears like magic, but it's not actually magic. So you can write your own procedures to do it. And as we've seen with the Python UDF capability that we've brought into 11.5, you can have user-defined functions that do that, or the user-defined aggregate capability that came in 11.1. But realistically, a lot of the time we'll go out to another tool. So we have SPSS from IBM as a very powerful statistical tool. MATLAB is another one that's very popular with data scientists. And then there's the world's most popular data science tool, Excel, which is used for all kinds of tasks, never envisaged, I think, by its creators. A bit like what happens on the mainframe. Nobody ever expected it would still be doing all this many years later. But increasingly, what data scientists are heading towards, less so much custom-built tools and more towards programming languages and writing their own applications. So a few of them mentioned there, but as we know, we can integrate these with DB2 as well. And I'll get to talk about Python a little bit now, because Python has emerged over the last probably 5 years as the de facto language, or certainly the most popular language for doing data science. Previously it was OR, and OR is very popular with statisticians, but a lot of data scientists are not statisticians by trade or by training. So they've tended to go with Python, because it's an extremely easy language to understand. Now, I started my career as a software engineer, so I studied C and C++ and Java, was used to the structure, and when I went to Python, I was like, where's the structure? Where's my curly braces and things like that? So it does away with a lot of those things, and it's very powerful, very easy to use. And I think what's particularly powerful is a lot of the APIs and other add-ons around it are extremely easy to use once you get the hang of them. And it has a huge amount of support from the community and a huge amount of integration from other big players. So AI learning frameworks like TensorFlow, which is coming out of Google, supports Python as kind of its primary language. It's very good at doing visualization, which is extremely important when you're doing anything statistics. It's graphing some of the diagrams that were shown earlier in Paul's presentation. Visualizing data is so much easier than presenting tabular data. Where it gets a little bit complicated with AI is once you go beyond 3 dimensions, it's really hard for us as humans to perceive how we do that. And there's techniques where we can take higher dimensions and bring them down. But we have an IBM DB package maintained on GitHub, available on GitHub, that you can use to download and integrate with Python. So it's fully compliant with the relevant APIs. For a long time, it was slightly Wild West in Python with regard to database integration, but they have an API now, which we fully integrate with. The other thing that a lot of data scientists use is notebooks, specifically Jupyter notebooks. So again, coming from a software engineering background, when I found notebooks, I kind of went, what are notebooks? Where's the value? Until I started using them and saw how you could document code with them in markup. It's like comments on steroids. And they're really, really powerful tools to actually to document what you're doing, present your results, and all the time maintain the code in them as well. And again, there's been multiple notebook styles. So Jupyter was one of the first. There's been notebooks from Apache in the form of Zeppelin, but Jupyter notebooks tend to be the de facto. And depending on your tooling, there's a fairly high degree of drag and drop integration. So within some of our IBM tools around the Watson Studio tooling, you could define a data source, and then you can just drag and drop data sources onto your notebook essentially and have it created for you. Have the connection parameters and all that created for you. One of the very, very popular and very powerful tools, and I think very relevant to a DBA community or a database community, is Pandas. So Pandas is a way of sucking in data, any data, and representing it in tabular format. So that's a natural extension for us of considering it's not a stream, it's not a position in a file that I have to worry about. I don't have to create an in-memory structure for it. I tell pandas to read a file and it gives me back a table. And it can do lots of different things with the table. It can, we can easily access by row, by column. We can create we can use numerical indexes. We can create named indexes on it. And that's only the start of it. That's only where you get going with pandas.
If I get the pandas table and I change a row, is it written back to the database?
Not straight away, but it is written in memory. And if you have copies, memory copies of that, if you have what I would call pointers to that data, then that frame is maintained. But it's in memory until such time as you persist it. So again, useful in that you can, say, read in the data, play with it, but not actually touch the source. I'll get to a little bit more pandas in a minute. I did actually, when I gave this presentation before, I did actually use a notebook, but I was discouraged from using a live notebook and videos. I didn't realize we'd be recording this, so apologies for the static nature of this. But connecting to Db2, relatively straightforward. So that's we issue a connect, database, hostname, username, password. So that was to a warehouse virtual machine I was running on my laptop, so that's where all these samples come from. And then we can, as with any of the low-level APIs, we can execute SQL directly against it. We give it a connection, a SQL statement, and you get your results back. So in this case, this is a Python dictionary, whereby we have key value pairs. So that's a common construct used in Python, is to just have things as key value pairs. Just to show you an example of how we did that PCA comparison earlier. So this was the scikit version, calling the scikit APIs, and you can see from DB2 is not actually all that different. I issued a call to a procedure, which was this procedure with these parameters, and I got my result set back. So that was just very straightforward. When we get to pandas, pandas has a better way of accessing data than actually having to go and establish a DB connection. You establish the connection, and then you just tell pandas to go and read the data. In this case, read SQL from this table. So that can be a more complex SQL. In this case, there was only 1,500 rows in the table. There was no need to get any greater complexity on it. But it can be that simple. And then when we start to get into pandas and what you can do with pandas, this is where it gets quite nice. As a developer, and this is the power of Python, why people like it. If I just want to see a quick check, did everything load okay? I just call head, which by default gives me the first 5 rows in a very clean format that's easy to read, and just say, actually, yeah, that does look right.
Does it mean that you have a data table scan on that one?
Well, that data has been scanned and loaded into Python. So it's not doing it after the fact. The data has been presented to pandas, and it creates the table in memory from there. So that would have done a table scan because of what it is. But if we had a more complex query, it wouldn't necessarily be a table scan. Other nice things we can do with pandas, if we do a describe. If we do a describe, one of the handy things here is we get a count straight away. So we can say, oh look, none of my rows have missing values. Very, very quick check for EDA. Do I have missing data or not? Actually, in this case, no. For numeric values, mean and standard deviation, and interquartile range. They're very useful checks, very easy checks, and they're computed for you automatically. So again, it saves time. It's why people like working with it. And just to get a sense then, we can call info, which just gives us a sense of what category, what data types have we assigned to these things. They're very simple, small checks, but they actually make they accelerate the process quite quickly. A very useful feature of pandas, which we can replicate in SQL, but it's kind of doing SQL-like structures, is we can use slicing. So on a columnar basis, this works quite well in that we can say, just show me the data frame. So I have my data, which is, in this case, 12 columns, but I just want to see these 2 columns in a data frame, so I can just get those 2. More useful, easier to do than in SQL. So that's like SQL. We could just say in SQL, select fixed acidity and volatility, but that's a new query. This isn't a new query to the database. What we can do more readily is say, I want just to see one particular row, or I want to see a group of rows. In this case, so we always take row n to n minus 1. So that's a very quick, we can just extract the rows more easily that we want to deal with. A little bit harder to do that in SQL without putting an OLAP function over it and then putting a where clause on the results of the OLAP function. Normalization in pandas, if we want to, so normalization could be something as simple as dividing by the total number of samples, or doing some other class of manipulation. So if you have a data value that's represented by, if it's encoded in some way, that what we actually mean when we've written 1, 2, 3, or 4, or 5, we actually mean it to be a multiple of that. We can simply multiply a value by a constant, or do any other kind of manipulation on that number. And there's this concept down here. This is what's called a lambda function. It's an anonymous function. I just use it once, like a macro, in a sense, an in-place macro. The other thing data scientists do a lot, which Db2 isn't as good at, or isn't really good, it doesn't really have any capability on, is visualization. So pandas makes it very easy to do a visualization. You just call a hist function or a bar function, and it draws the data for you. You don't have to get any more complex than that. And as to writing it back, well, there's so we had a read SQL command. We have a toSQL command. So we read the data in, we manipulate the data, and if we want, we can write it back. Now, I stand to be corrected on this, but in my experiments with this, it didn't always work that well. Mainly because what it does is you have two choices. It either appends or it overwrites. And if you have any kind of referential integrity on the table, or actually even if you don't have referential integrity, that can make a mess of your underlying table very quickly. So if I have, this was the value I read in a SQL, I added a third column to it, and this is what happened to my table when I wrote it out to SQL. So I ended up with duplicates. So if you were using Python at the moment, or pandas specifically, I would write back the data using proper calls, using update or something like that. It's not as efficient, it's not as cool to write it as one simple command, but you don't want to end up with this situation here either.
And we talked about the importance of data quality.
Yes. Which is, I suppose, that leads to a good point. Yes, you can do this stuff from DB2. Be careful. Because your data scientists won't necessarily know that they, or care, that they're doing this to your database.
Just select privileges.
Exactly. Just select privileges, or with a couple of declared temporary tables behind them, or something like that. So, just to wrap it up.
Could you go one slide back? So it read the data and wrote all the data back?
Yes.
Okay.
So it read the data. So it's pretty much, so the question was about it reads and then it wrote all of the data back. So the read is as we'd expect it to select, so it just pulls in the rows that are in the table. For when it does the toSQL, what it's doing is an insert, or else it's doing a truncate and insert. But it's not a merge, it's not an update, and that's why it's dangerous at the moment. As I say, I stand to be corrected. There's probably smarter ways around doing this, but I didn't find them easily, which is why I'd caution against it. If there was a primary key, you would get, what happens if there's a primary key? If there's a primary key, you would end up with a lot of exceptions, because the database engine would return, DB2 would return a SQL error, which would get propagated back, but it wouldn't be gracefully handled in that sense.
But the third row would be written back to the data, and then I need to find out which garbage I put in.
Yes. Yeah. So, to wrap up, kind of, when would we use DB2? Or when do I see value in DB2? Because these are, at the end of the day, just my opinions, really. So, I'd consider using DB2 when there's large data sets involved, when there's terabytes or hundreds of gigabytes of information that that the data scientists are looking to access. Easier to bring them to the data than the other way around. And they can also see then if they can use their EDA techniques to reduce the scope of the amount of data that they want to pull out.
Just a question with that pandas workbook, could I do something like fetch first 10,000
You could, because the read SQL literally just passes whatever SQL you send into the database. So I'm not sure if there's an actual, there might be some parameters you could issue to pandas, but it's free-form SQL, so it's whatever SQL you can generate. Yeah. If you have any restricted data sets, I think this is a very strong use case for DB2, for doing the data EDA in the database, because then you can, again, you can narrow down the scope of what's required. You can look to have them. They can access the sensitive data in place, but then not remove the sensitive data from the database. So that might be anything personally identifiable, like gender, address, name. See if it's a value in their model, and then take the bits that are important. For simple regression problems, it's amazing the amount of problems and benefit that can be derived from a simple linear regression. I was talking to some of our data science elite people there during the summer, and they said the amount of customers who are only just starting on this and who they are very happy to see just a simple regression problem. Neural nets are really cool and they're really exciting, but you can solve an awful lot of problems by using something simpler. And similarly, any simple classification problems. So even if you're just exploring, trying to identify groupings of customers, groupings of transactions or something like that, you can do all that in DB2. As a quick wrap up, as a nod to some of the other capabilities that you'll see around, so IBM are positioning DB2 for AI. So we have these things in DB2. There's some other things coming around as well. So I've talked about the IDAX tools. Callisto has a session coming up now shortly. Callisto is Arte, our STSM for database performance. He's going to talk about how we're applying machine learning inside DB2 to the query optimizer. And again, this is what AI does. It's an optimization tool as much as it is anything else. And that session is coming up shortly. And there's external tools that we're starting to develop as well, and to bring some of this power. So they're not built into DB2, but they're coming along under the DB2 name. And that's the Augmented Explorer for doing kind of, instead of writing it in pandas, using natural language query to explore some of this. And that's the kind of plot you can generate anyway. And we have some demos around graph analytics, which we're hoping to roll out in the next little while as well. Apologies, this particular slide is not in the deck, if you're downloading the deck, because I only became aware of this site yesterday. But on ibm.biz, learn DB2, there's a section for code patterns, and there's some examples there of if you want to explore this further. Specifically, there's an example there of predicting home values using Python. And it shows you how you can use some of these IDAX functions to do a regression solution in DB2. So, just to summarize, so the core of AI, the core to succeeding with AI is having access to data. And relational databases, DB2 has that data. And you can use DB2 because what DB2 delivers, what a database delivers, is quality of data, the quantity of data that's needed, a trusted data source, and also the capability to do local processing on the data. And where that doesn't work, we can integrate with other tools as well. So I'd say to you, if you are looking at data science, a lot of what we need to consider as DB2 professionals, I think, is to maintain not just that we're data people, but that we're relevant in the AI world. And DB2 is relevant in this world because we have the tooling around it. So I'd say your platform is relevant, your skills are relevant, and be part of that AI conversation. So thank you very much. I hope you have a very good afternoon and enjoy the rest of the conference.
Thank you, Mark, for your presentation. Before you leave the room, there are questions, actually. More questions. More questions, yeah.
I would like to know, you mentioned that some of those AI capabilities are just available in the clouds.
They're not just in the cloud, where they're integrated with, they're built in at the moment. So they're on the DB2 warehouse container images. So that means warehouse on cloud, it means IaaS, and it means the standalone Docker container that you can download.
Okay, but if I have customers who just use on-premise DB2?
They're not in the GA versions yet. They're not in the on-premise versions yet. I'm not sure what the roadmap for that is. It was something I was trying to find out, didn't get an answer on yet.
The second question, you have shown this chart of comparison, scanning data with when you look on the database level, exact of doing an outside.
me see. That chart?
No, it's with a bar chart.
Oh, the bar charts.
There's a big SQL and
Yeah.
exactly this one. In which times we are talking about? Are these 10 minutes or?
They're not. I think if I recall rightly, I can't apologize. I was trying to find the background on this one. I had it and I lost it. What I would say is don't so much interpret them as numbers, but look at the magnitudes difference between them.
But I have customers, let's say, let's say these are 10 minutes on the left bar chart. They don't care if they take 10 minutes or 2 minutes. They say, we would spend 1 week just to see if the data are reasonable or not. So they
Yeah.
are passionate about such a high improvement when we are talking about minutes.
Yes.
If this would be 10 hours compared to 2 hours,
Yeah.
then they would say, okay, this might be.
Yeah, I understand. Yeah, I should update the chart on that one. I'll find it again. Yes.
Question on, integration, maybe future integration between, you spoke about pandas
Yeah.
versus data. And, well, I try to formulate the question in a concrete example, the head function you mentioned, your data frame. Well, that's already loaded, data loaded from Db2 into
It is, yes.
Python. Is there maybe already, or plans to, from IBM plans to integrate it in the sense that you have a kind of a virtual table or a data frame and the head function goes only at that moment and do the fetch first?
I understand. I think, so technically Pandas isn't actually the one talking to the database. Pandas talks to another Python API, SQL Engine, SQL Alchemy, and that in turn talks to the database. That would make sense.
And that intermediate layer, you could, well,
That's where they.
an IBM building block.
Well, SQL Alchemy is not ours. SQL Alchemy is an open source project and integrates with lots of other databases. I have seen things in the roadmap for new updates with SQL Alchemy. I'm not aware if we're doing that, but it would be a good idea. So I'll certainly look into it. And
It's not there yet, or it's there?
I'm not aware of it, but I haven't explored it to that level. So apologies, I can't say more.
I know, for example, there was this big R
Yes.
project which did similar things, I think, in Arden. So I was wondering whether.
Yeah, I think one of the challenges for any company, I think particularly, well, any company, whether it's ourselves, Microsoft, somebody else, is the community very quickly changes. If you go back 5 years, OR was where it was at. OR was going to be the next thing. And fast forward 2 years, and Python was where it is. And now, actually, other tools, I can't remember, there's other tools in academia that are coming up and Go is becoming a hugely popular language. And it's very difficult to have a product roadmap and with all of the things, because you place an investment that takes a year to fulfill, or 6 months to fulfill, and the crowd has moved on. It's like going to a party and you find everybody's gone on to another bar and haven't told you where they're going yet. So, you're always in catch-up mode. But I'll find out if I can. I'll get your details and I'll find out if I can see if there's anything on that. Any other questions?
Some years ago, data mining was very popular. Is it part of that machine learning, or would you do?
Honestly, I can't answer that question. I never did. I was never actively engaged in data mining to the level that I can understand.
Okay, not that big.
Sorry about that. Thank you very much, everyone.
Thank you very much.
Bye.